I've built more than 100 GPU servers in the last couple years, and I'm still amazed at the engineering that goes into a high-end GPU server. How can a single server support 8 GPUs, 10 NICs, and 16 NVMe drives? In order to support this many devices, a server needs to have multiple PCIe switches that all aggregate PCIe bandwidth back to the CPUs. Today, I'm going to show you how this is laid out in a typical H200 server. Every server has 4 PCIe switchboards built into it. These PCIe switchboards connect back to the motherboard at 32 lanes of PCIe Gen 5. From those switchboards, they're hosting 2 GPUs, 2 to 3 NICs, and up to 4 NVMe drives. That oversubscription ratio is possible because all of the PCIe bandwidth flowing through those devices typically can stay device to device, meaning that the CPU never needs to get involved in any of that traffic. The biggest driver of communication inside of these nodes is typically the GPUs. That's why all of the OEMs have their own baseboards. NVIDIA's is called NVLink, and it's a series of switches directly on the baseboard that allow the GPUs to communicate with each other at insane bandwidths. The same concept is used with the NICs. So those NICs are connected to the same PSBs as the GPU baseboard is, which allows GPUs to send data directly to the NICs and out to other nodes in a cluster without needing to weigh too heavily on the CPUs. This is the basis for these large scale-out GPU clusters that you always hear about. For a normal Intel server CPU that would go into something like this, you'd typically only get 80 lanes of PCIe connectivity per CPU. With this PCIe switching setup, you can push it to almost 300 lanes of PCIe connectivity between the motherboard and all of the devices connected to these PCIe switches. What this enables is massive scale-out GPU clusters. Those clusters can be used for training or inference, and it's the basis of all of the reference architectures that the big OEMs put out. NVIDIA reference architecture for H200 clusters has 3,200 gigabits of bandwidth between each node. And that's typically done with either dual port 200 gig NICs or single port 400 gig NICs. In the next generation of GPUs, you're seeing clusters with double that. We do have 800 gig NICs and 800 gig switches that interconnect all of these things. The servers that I used to build were a lot simpler than this. We would just wire up 8 GPUs directly to a motherboard that would use 128 lanes of PCIe Gen 4. And then with the remaining PCIe connectivity, we would handle the network connection, and we'd have a couple NVMe drives. If we wanted to do something where we were balancing GPU connectivity with network connectivity, we would need to sacrifice the number of GPUs that we could actually support in one of these servers so that we could have enough NICs to be able to actually send data out as fast as we're putting it into the GPUs. With this PCIe switching architecture, you don't need to do anything like that. You can just keep everything in the PCIe complex and allow the devices to communicate with each other without needing to have a CPU in the mix. I can imagine at this point, you're wondering how much does one of these things cost? And the quick answer is for an H200 server, it's $200,000 to $250,000, depending on whether you're getting it new, whether you're getting it from a tier 1 server manufacturer, or just a company that assembles these things and sells them as hardware. The new nodes, the B200s and the B300s, they're more expensive. I've seen those sold everywhere from $325,000 a node to $425,000 a node. There's obviously a lot going on with memory prices right now that drive a lot of that discrepancy. But even between server manufacturers, like a tier 1 vendor will sell the same hardware for $25,000 to $50,000 more expensive than another. If you enjoyed this, please let me know. I love talking about technical stuff like this and would love to do more of it in the future.